Section 1.6, Notation and Mathematical Background. It is assumed the reader has an understanding of basic mathematical notation and operations, including sets, function notation, basic probability, and basic matrix algebra. Appendix A reviews key results from multivariate calculus that are used, but other basics are assumed known. We now highlight a few notational elements that we use throughout, and you may also consult the notes, references, and further details at the end of the chapter for suggestions of a few resources that may help with the review. Vectors are in general elements of R superscript n, with n being some positive integer. We can denote a vector u in Rn as u equals u sub 1 up to u sub n, where the scalar ui is the ith coordinate of the vector. Written in this tuple form, we consider the vector as a column vector. That is, we may consider, for example, a matrix A, an m by n matrix A, and then have the matrix vector product V equals AU, with V being V1 through Vm, an element of Rn, and each Vi given by Vi being the sum from j going 1 to n of Aij Uj. So Vi is obtained by multiplying the vector by the ith row of the matrix A. An alternative way to represent a vector is using square brackets, in which case we take its orientation literally. For example, W equaling W1 ... up to Wm in square brackets is a row vector, and its transpose, W transposed, is a column vector and an element of Rn. In this case, we may, for example, consider the vector matrix product W equals, X equals Wa, which yields X, an m-dimensional row vector. Hence, in summary, with our vector notation for U in Rn, we have U being the column, or the row transposed, or the tuple. Some key vectors we consider are the bold 1 in Rn, which is a vector of all ones. Similar 0 can be taken as a vector of all zeros. However, the same symbol 0 is clearly also used for scalars and matrices, with the actual meaning clear from context. There are also unit vectors, E sub I, with dimension taken from context, and I being 1 to n, in case they are n-dimensional. Each such unit vector has 0 entries everywhere, except for 1 in the ith coordinate. So as an example of this notation, see that the identity matrix, I being an element of R n by n, can be represented as a sum of outer products, where each outer product is the column EI multiplied by EI transposed. That's the identity matrix. The norm is often used, and unless stated otherwise, it is the vector L2 norm. That is, for a vector U in Rn, the norm of U is the square root of U transposed U. Similarly, the norm squared is simply U transposed U. Surprisingly, beyond matrix vector arithmetic, norms, and a few basic operations, we only seldom use linear algebra machinery such as eigenvalues and the singular value decomposition. This is because most of the book is focused on the basic mathematical engineering of deep learning, which at its core does not use very sophisticated mathematics, but rather employs basic mathematical concepts to create sophisticated models. We thus leave it to the reader to seek a self-refresher on such topics as they arise. For example, some of our discussion of unsupervised learning in Chapter 2 builds on understanding of linear algebra. However, these topics are in general tangential to the core material of the book. In terms of concepts of optimization theory, Chapter 4 covers these in a self-contained manner that does not require further background beyond a few multivariate calculus results reviewed in Appendix A. Hence, for example, convexity is briefly introduced and summarized directly in Chapter 4. At certain points, the reader may want to dig deeper and review topics individually elsewhere. Finally, in terms of probabilistic concepts, it is assumed the reader is aware of the informal definition of probability, P, and basics of random variables. This also includes the expectation, E of x of a random variable x, the variance denoted var, and covariance. Similarly to the linear algebra concepts, we do not make heavy use of probability theory. However, certain probabilistic computations occasionally arise. So thank you. That concludes the last section of this chapter. That was section 1.6. I hope you found this video useful. As discussed, you can also look at Appendix A, which actually gives you quite an extensive review of vector and calculus used in the book. Leave any comments below. Thank you.